So this next session, we're going to look at the future of cement processing. So we've looked at this to some extent in the other sessions earlier today, but we're going to look at things a little bit more specifically and talk about some of the technology paths available. So Matthias, who you already know from several sessions and from his chairing the last session. We also have Daniel Stack, who is the co-founder and CEO of Electrified Thermal Solutions. So Electrified Thermal Solutions are all about thermal storage. And Daniel, maybe you can take it away and explain to us what your company does and why it's relevant for cement.
Sure. Thanks, Ian. So, yeah, happy to be here at WCA 2023. As was already said, Dan Stack, co-founder and CEO of Electrified Thermal Solutions. We founded this company. It's an MIT spin-out. We've kicked it off around 2 years ago. The tech that underpins it is roughly 10 years in the making now, mostly during my time at MIT. And we launched the company with the mission of decarbonizing industry with electrified heat. And obviously cement is one of the hardest to abate sectors. So I think that what we're working on here is uniquely relevant and a unique focus of ours in the cement space. And so if we kind of identify the pain point that pretty much all industry feels right now, is that there's no affordable way to decarbonize your heat. There's no affordable option for it. And if we kind of identify three main features here, the good news first is that our zero carbon electricity coming online overall is pretty cheap. Solar and wind have gotten very inexpensive. You can find off-peak nuclear and hydro plants in a variety of areas around the world. What's expensive is firming that energy. That is making it there when you need it. Whether it's in a battery or generating hydrogen with it, it's a very expensive conversion process that 6 or 10x is the cost of the electricity. And then finally, if you're gonna store it for later, you better get it out as heat. If you're an industrial user, if you wanna run your cement kiln, your calcining step, you need high temperatures. So what we developed is something we call the Joule Hive thermal battery. It is a box that takes in electricity, converts and stores it as heat that we can get out on demand at flame temperatures, and we can pipe it directly into furnaces, kilns, boilers, even power turbines to reproduce electricity when you like, all in place of the fossil fuels that you normally consume. And so we can store up electricity from intermittent solar or wind or off-peak nuclear or hydro, and that can come in intermittently, come in when it's cheap, when it's abundant, when it's available, but what comes out is constant flame temperature heat. And the breakthrough that allows us to do this at these high temps and at an affordable price point is what we call the building blocks of industrial decarbonization, our main breakthrough, electrically conductive fire bricks. And I have one here that you can see later as long as you don't steal it and as long as you leave a business card. And so these bricks are what we were working on at MIT. And basically looking at the problem of electrified heat, we saw that the main shortcoming was the electric heating technologies. Electric heaters today can't take the heat, can't hold up for the longevity that industry needs. They weren't designed to replace fossil fuels. And so what we looked towards was materials that can take the heat and last for decades when treated right, and that's fire bricks. And we made these bricks with semiconductor doping. We made them into electric heaters, which we can stack up to massive scales, say in the form of a shipping container, or towel into a tower form that can operate as a giant electric heater, a giant thermal store, and a giant heat exchanger, all in one, built from cheap, abundant bricks that have no metals that are going to oxidize or wear out, and it can last for decades, provide flame temperature heat. And because of the scalability of this approach, we can scale to the largest, hottest industrial needs. And so we're starting with a shipping container style system next year. Right now we have our elevator-sized box where we're stacking the bricks up and running them at 1700 Celsius right now. And ultimately where we head is up to the hundreds of megawatts output and gigawatt hours of storage. And that's the kind of scales we would need for the cement industry to replace your heat to your calcining steps and your rotary kiln. And as far as the difference maker, the bricks themselves, we didn't arrive here overnight. we found that we needed something that could go really hot, 1800 Celsius, that could be scalable, and it could be low cost. And what we basically recognized was that today's electric heaters couldn't do it. Traditional metallics, ceramics, some folks are trying to use graphite, things that aren't really up to the task. They all have a shortcoming on cost, scalability, or temperature that wouldn't be able to serve the cement industry in all the ways that it needs. So because our bricks are oxides, they don't oxidize, they don't burn out like traditional heaters. And because they can operate at flame temperatures in air or in CO2, as we'll talk about a bit more later, we can avoid the need for inert environments, extra capex of heat exchangers, et cetera. So the first system that we're building, I mentioned, is a shipping container. It's just a few megawatts in, a few megawatts out, and can provide constant high temperature heat to a variety of applications. It's a little small for the cement industry out the gates, but as we mentioned, where we're heading is those towers. And so this is just the beginning, and we have a variety of technologies that can kind of all be built from these bricks to support industry. We have the boxes, the towers. We can even build hot walls out of this that just provide electric heat. There's no storage, which means it doesn't synergize with renewables. It doesn't synergize with off-peak cheap electricity, but it can provide that to industrials as well. We can even run a turbine, so we can provide round-trip electricity if you like as well. So this is the suite of options we have to support electrification of industry. But if we talk about applying this to the hardest to abate industries, like cement, there's a scheme that we think has great promise, but with lots of work to be done. But basically, by using electrified heat, we can enable flame temperature and flame intensity heat delivery and pure CO2 streams, or near pure, we qualified that a bit earlier, by basically looping the CO2 through our system that is today generated by your clinker, by your calcination step. And this is something that's relatively agnostic scheme we have here that we've been looking at to apply to blast furnaces, ethane crackers, glass furnaces as well. Everyone's a little different, but the main inspiration for this was the cement industry, which is that CO2 comes through the Joule Hive and gets heated up very hot, up to 1800 Celsius as you need. We flow that CO2 into your process. Some of this could go to your pre-calciner, some of this could go to your rotary kiln. And we can deliver that at the high temps you need radiatively. You generate more CO2 coming out of that. We clean it up. Some of it goes to the pipeline, where it could be sequestered or used for utilization. Maybe clean up a bit more to get to those higher purities, but you're coming out at high 90s% purity because we're not adding any air. You don't need any combustion, therefore you don't need any new gases. And then we recirc the rest and run it back through the Joule Hive again. And so there's no need to separate nitrogen, and so we can cut down dramatically on cost while providing zero carbon heat. So no fossil fuel combustion and relatively easy capture is the dream. And this is a scheme we're trying to apply to multiple industries, but we are engaging heavily with the cement ecosystem right now, and we'd love to talk more to folks about this. And I'm sure there's plenty of questions and points to roast me on, given the very high caliber folks we have in the room on CO2 purities and approaches to this. So with that, happy to talk more. Thanks.
Thank you, Daniel. Daniel, I'd like to ask you a couple of questions. We'll come to questions from the audience later on. But I wonder if you've... so one of the use cases that I think perhaps is easiest to get your mind around as a cement guy is probably using this for the pre-calciner.
Yeah.
I wondered if you'd done any sort of modeling of what the potential savings could be in a particular market, given the way that electricity is priced in Europe or in North America. If you use the low-cost renewable energy when there's a lot of it, and then use it to power the pre-calciner. Have you done any sort of in principle modeling of how that costing would work?
Certainly. So most generically, and yes, as a starting point, we've been in our talks with cement companies. We had a webinar with Boots Unichim where we showcased some of these points, and we were also on the CEMEX list of promising technologies. And in those discussions, putting heat straight into the pre-calciners, something that could potentially offset roughly 20% of emissions. As far as the market behavior, electricity, market and savings, it fully depends on where you are. But, generically speaking, if we just look at electricity prices and how we operate the system, the economic payback is kind of agnostic to the industry. So with that said, we did analyses domestically in the U.S. In areas of the Midwest where there's a lot of negative priced electricity. And the punchline was, in certain areas, including where some cement plants are, electricity was below the price of natural gas roughly 50% of the time. And with that, we could store that and run later off of it and replace 80% of the fossil fuels consumption and have paybacks in less than 5 years. So that's a market that's opening up. It's not everywhere. Some areas it will not pay back at all, mind you. But the markets are opening up today for electrified heat if you can do the storage. If you can't, then you're going to be a price taker and it will not be as good for you.
Right. And if you were starting a project with a cement plant, if one of these guys here today says, okay, let's go ahead and start a project, then what would be involved in that? And do you have any idea as to how long that might take?
Certainly. So first off, please get in touch. So we're working on that first demonstration unit, deploying next year. And what we're doing with that unit is running lots of different operating campaigns. For example, partial replacement of heat that would go into pre-calciner. We emulate what temperatures do you want out, what flow rates do you want out, so that in the following years we could hook up to a plant, kind of a first-of-a-kind integration that allows you to start getting the operational experience, and getting comfortable with it. And then in the meantime, 2028, I think, is what we've said for the tallest towers. Maybe 2027 was the first one, late 2027, early 2028, where we're hitting the, many tens of megawatts or approaching 100 megawatt scale, where we could start to do serious replacement of potentially full calciner heat.
Okay, thank you, Daniel. Matthias, let's come to you next. And so, Matthias, you're going to talk to us, I think, about the potential that KHD has in terms of the future of cement processing.
Yes, maybe, but actually I've decided not to be too commercial here. Okay, so what is the future of cement processing going to be like? That's what I've entitled my presentation here. And I'd like to recap a lot of things we have been talking about throughout the day already. And I think what is describing the situation of cement producers these days, there's one term that is uncertainty, right? It's very tough to make decisions in an environment where you don't know exactly what you should do because the technology is not there, the business model is not there. Many things are lacking for traditional decision making. Still, we have to get going and have to do something. So what do we know? We know that the cement sector needs to decarbonize from now on and needs to achieve net zero by 2050. And this is really carved in stone. I've been working for product development for 30 years. And in product development, there's one golden rule. You'll have to connect the market pull with the technology push. So the market wants something and the technology enables something. If you can marry those two, you'll have a good product. So that's the classical thinking of product development. In this case, it's even one level higher in its level of stringency. It's not the market pulling something from the equipment suppliers, it's the international political community that has signed the Paris Agreement. 196 countries have signed the Paris Agreement, and they have committed to keep the warming of the global average Earth temperature to limit it with 1.5 Kelvin or maximum 2 Kelvin. That is the political will, and 196 countries have signed to it. So the governments that have signed this will apply instruments to the markets. In Europe, for example, it's going to be the emission trading system. In the US, it's carbon tax. Whatever comes, but there will be instruments applied to the markets, and the markets need to solve this in connection with the technology suppliers. So this is really a very unique situation, and there is no way around it. We have to decarbonize by 2050. There is a campaign run by a non-state actor that is called Race to Zero. And this is an assembly of more than 11,000 members of all sectors in the UN, and it's chaired by the UN High Climate Champions. So that is not just any organization. It's one of the basic organizations looking into things and trying to find out what is necessary and what needs to be done. And this Race to Zero campaign says we have to halve the emissions by 2030. And they also say at the end of 2050, when the transformation has been done, we will have spent 125 trillion euro. Take a second to judge the size of what we're talking about. This is, of course, not only cement, but this is the whole industry, all sectors. But if cement is good for 8%, you can judge maybe 8% of that. So we're talking about a huge investment wave to be coming up and to be necessary. And they also say the investment from now, and these are statements from 2020, from now to 2025 needs to triple compared to what we've done in the last 5 years. Now, it doesn't take much to know that now in 2023, we are not even halfway through what we should have done. We had this morning as well. So we're lacking behind. We're much behind the plan, but still, 2050 target is fixed. We need to get there. So we have to accelerate, and this will lead to a very, very dynamic situation. What we don't know, and that is, I think, what everybody can subscribe to, how exactly should we do it? This is the big question. All right. Most of you know this picture, probably. This is taken from the first roadmap on decarbonization issued by the International Energy Agency. And I still like it very much because it boils down our levers to only 4 categories. The first category we can work on is thermal efficiency. The second one is fuel switching. The third one is reduction of clinker to cement ratio. And the fourth one is innovative technologies. You see by the wording, this is already some 15 years old. Meanwhile, everybody is talking about alternative fuels instead of fuel switching. Everybody is talking about SCMs and calcined clay instead of reduction of clinker to cement ratio, even though it's not wrong. But it's just, you feel the wording is not up to date. But still, it shows very much an estimation of what is the potential of these levers. The question is, what can you do in terms of applying these levers? A more modern roadmap is published by the GCCA just recently, maybe 1.5 years ago, and you see the different potentials in the different fields for decarbonizing across the whole value chain from cement to concrete and civil construction. I'm not going into each and every number of these. I'm sure you know these roadmap and the numbers yourself pretty well. So, seen from above, it all looks easy. There are these roadmaps, and they show what is possible in what kind of activity field. But what does it mean for each and any specific plant? Because what you are going to do is going to be highly specific according to a number of characteristics of your production site, most of them being logistic. Are you close to this? Are you far away from that? Do you have access to this? Can you dispose of that? All these kind of things. So what does it mean for each and any specific plant? Now, some 5 years ago, I had the ambition to create a map of technologies. This is how far I got until I stopped. This just briefly should illustrate in a structured way what kind of technological pathways are possible for the cement industry. Like, for example, we can work on the production process, and we can work on the pyro process and the grinding process. We can apply lower energy consumption technologies. We can do pre-processing of spent concrete, for example. In the field of pyro process, we would have conventional pyro processes which we could operate with low carbon fuels. That is what is called not post-combustion, but pre-combustion. So we take out the carbon from the fuels. We can use biogas. We can use hydrogen theoretically. I can let you know my point of view on that. Pre-combustion, we can use concentrated solar power. We could use electrified produced heat, all kinds of things. I won't take you through all those boxes. It just shows that, when talking about technical possibilities for decarbonizing a cement plant, the door is opened to a huge field of technologies, and that is applying all kinds of energy generation, energy transformation, pre-processing, post-processing, new type of reactors, new type of processes, endless. After each and any box on the next level, there is still a multitude of options. So what is the best solution for you? That is the big question. All right. So we are obviously in a transition, in a transformation process. We know we have to go, but we don't know where. One important question is, what kind of technology will be available when? And what is the potential of that technology? And I've tried to put that onto a diagram. You see on the horizontal axis, the time axis, and on the vertical axis, you see the cost per ton of CO2 mitigated. Now, what you're going to see now is a bubble diagram with the size of the bubbles representing the potential of CO2 mitigation, and the position of the bubble will say how much it could contribute to CO2 mitigation and when it could be available. Now, this can never be exact, right? I beg everybody's pardon. This is only an estimation. But one thing is very clear. Real-time optimizers, RTO, formerly known as expert systems, or plant optimizers, whatever you call it. The typo these days is RTO, real-time optimizers. The beauty of that is they reduce your production costs at the same time. You have usually an ROI of 1 year or 2 years. If you have a huge system, maybe 3 years, but you will cash in later all the more. So real-time optimizers is really something that is good for you, reducing cost and reducing CO2 emissions. Next thing, we've been talking all day, alternative fuels. Same thing. You'll have an ROI maybe between 2 and 5 or 2 and 6 years. In the long run, it's a good decision to go for higher TSR rates and using alternative fuels. It can reduce your operating cost massively. Next thing, alternative raw materials, and that is highly specific. Depending on what you're talking about, it could be costly, it could be less costly, but on global scale, it wouldn't contribute much. You might have one plant that is very appropriate and can solve all its problem at one blow by using alternative raw materials, but the whole cement industry in total wouldn't be able to cash in benefits largely. Then we have the whole field of supplementary cementitious materials, reducing clinker ratio, and this is of course highly connected to the question of calcined clay, because calcined clay is a very appropriate cementitious, supplementary cementitious material, because it's available almost everywhere in the world and very suitable for producing SCM. Then we have already available today partial post-combustion CCO. Partial. Why partial? Because the waste heat you have available in a cement plant is good for only 10% capture. If you want to have a full capture, then you have to put energy into the regenerator column, and you have to put something between 2.2 and 3 kilojoule per kilogram captured CO2, which is almost as much as you use for producing your clinker. So this is only feasible if you do as much capture as you have waste energy available in the cement plant. Then we have calcium looping, also under trial these days. Can be beneficial for some plant. I think as a total solution for everything, I'm a bit skeptical. Then we have post-combustion CCUS. That is what I refer to, the total capture, but it is very expensive because you have to put all that energy in. If we use it, it can have a huge bubble, a huge impact. But bigger is the potential for oxyfuel CCUS. The difference being that oxyfuel process concentrates the CO2 and makes it easier to capture the CO2. So oxyfuel is at this moment the only contender known in sufficient TRL that could be decided to invest today. Indirect calcination, some of you may know the LILAC project, where you separate the gas coming from calcination from the exhaust gas coming from combustion in a two-type tubular reactor. Also an elegant solution, but it's only for partial capture because you can only take the calcination CO2, not the sintering CO2. Now, the big question mark, and maybe what we've heard before, electrification, maybe something else. People are busy working on it, on alternatives to oxyfuel CCUS as the contender for affordable, techno-commercially feasible capture technologies. Right. The good news is the first part, the path towards 2030, is clearly visible. And that is alternative fuels, SCMs, RTOs, reducing clinker in cement. Very simple, and it's always a good decision to go for that. Don't hustle into each and any adventure, but it's in principle the right decision to take. And every ton of CO2 saved today is worth more than 1 ton in the long run, because we're pushing this big heap of decarbonization necessity in front of us. We have to start eating it up. And we have to get going fast. But from 2030 onwards, it's still unclear. All right, short-term future, carbon reduction by 2030, halving the emissions by 2030. That is what is required according to Race to Zero and according to common sense. You can do that by energy efficiency increments, real-time optimizers, kiln and plant optimization. There's a lot of things to do, a lot of potential to be raised. Lowering clinker ratio in cement, composite cement, LC3 cement, calcined clay, all those terms are all well known. It requires maybe new thinking, but technologically it's all there. Alternative fuels, and specifically biogenic fuels. In the EU, we have to go from 40% as an average to 85% according to the roadmap of the VDZ. That is quite challenging, and even the European Union's cement plants are already quite advanced in this. It is quite a step forward, but we have to get going, and it's worth it. Alternative raw materials, we have, for example, developed processes for utilizing carbide slag or other industrial calcium-containing waste products. But these are niche solutions which need to be adapted for the specific case. We've done that for a couple of customers. As KHD, we've also, of course, a whole range of technologies for burning alternative fuels from 5% to 100% with external special reactors like what we call the pyrorotor or special burner technologies. We have grinding technologies that allows suitable grinding and with high fineness grinding for composite cements. So technological solutions are all there. I don't show you now the product portfolio of KHD just to make sure this is what we can deliver today, no question. But what we also need to do now in preparation for what is going to come up after 2030 is to start piloting installations for these novel technologies. Amine scrubbing, post-combustion MEA, as I said, techno-commercially only possible up to 15% partial streams. Otherwise, it's not feasible. So we have to develop into oxy-fuel kilns. We deliver oxy-fuel kilns. We've heard from ThyssenKrupp, they are also delivering oxy-fuel kilns. So it is a technology that is ready to be projected, ready to be decided upon. It is available. Even though it will not be such a standard technology like you have in a conventional plant. Carbon capture technologies, yes, predominantly everybody's talking about MEA scrubbing, amine scrubbing, but there are lots of different other technologies available like pressure swing absorption, temperature swing absorption, pressure-temperature swing absorption, membrane supported, metal oxide framework. Hundreds. And we are about to find out what is appropriate in what case. And then electrification, calciner and kiln. Yes, electrification, a huge challenge ahead. The transport of the energy in the sufficient density is a big problem. Maybe you can find a solution, maybe we can find a solution, maybe we can find a solution together, I don't know. Electrification, if we get it done, is really a step forward because we're producing a pure CO2 stream and we don't need to clean the gas from combustion residues. So that's a good step forward. All right, the long-term future, full decarbonization is a very complex issue and requires downstream carbon routes. As I said this morning, this is the most challenging step in decarbonization. Downstream carbon routes and value chains, what to do with the carbon, that is a prerequisite for any investment in a capture plant. Storage utilization, circular business models, logistics, infrastructure, all these are questions that need to be answered. Novel energy scenarios, we need renewable emission-free energy supply, and we need integrated energy utilization scenarios, and not only maybe for the cement plant, but maybe for a conglomerate of industrial plants, like a cement plant right next to a chemical plant, right next to a steel plant. We need to integrate that in terms of mass flows and in terms of energy utilization. We need sector coupling, as I alluded to earlier. We need the synergetic utilization of feedstock, intermediate products, and energy streams. And we need to adapt our market setups for the new economy, for the new business models. We will see that cost and price levels will change unavoidably. And we're afraid that if cement price goes up double, we have to close our plant. I don't think that. I'm sure it's not going to happen like that. Yes, prices will increase, cost will increase. We will come up at completely different KPIs, which we today may find inappropriate and prohibitive for our business. But the market will absorb it because There is no future without cement, and there is no cement without decarbonization. And if it costs something, we have to keep the additional cost down as much as possible. But if it costs something, it costs something. The market will absorb it. There is no other building material like cement with such a low embodied carbon, embodied energy, and eco-friendliness. Even if people talk about wood, wood cannot replace concrete. Steel, plastics, whatever you take, has higher carbon than cement. Cement only has this bad reputation of 8% because of the sheer mass, because of the 4.5 gigatons per year. That's where the problem comes from. And in the end, what we need, we discussed this morning very much, what needs to be done. I believe we need much more political pressure. We need a clear roadmap, clear guideline for the industry, for the economy, in order to be sure to make decisions even at this, in wide scales, uncertain environment. Otherwise, we will not be making it till 2050. Let's discuss. Thank you very much.
So Matthias, I'm going to ask you a hydrogen question in a minute. So I will come to the audience. I'm just going to give Matthias a question on hydrogen, and then I will come to the audience for your questions. So Matthias, do tell us your views on hydrogen.
Yeah, I announced it, and now I owe it. Hydrogen is a much debated subject. For me, it's unbelievable that we will be using hydrogen as a large-scale energy source. Because if we use hydrogen, it needs to be green hydrogen. So what do? We take solar energy or wind energy or whatever, produce electricity with it, and instead of directly using the electricity, we're going a detour by producing hydrogen, thereby losing 90% of the energy because we try to split the most stable element on Earth, water, into hydrogen and oxygen, just to take that hydrogen and put it with oxygen again, thereby having lost 90% of the primary energy. I have a real hard time to believe that cement can absorb this. I've made an estimation. If I operate a cement plant with hydrogen, then the production costs go up 20-fold. So, I mean, there are lots of side conditions which you'd have to discuss in detail, but no. Hydrogen is good for processes, industrial processes who use that as a feedstock at the same time, but not as an energy carrier.
Okay, thank you for that. So, questions. Who would like to ask questions to either Daniel or Matthias?
Electrolyzers are up to 70% efficient. Could you explain why you're going to lose 90% of your energy? Yeah. So when you take water and you split it.
Oh, the electrolyzer, right?
That's right. Yeah, that's what I said. Electrolyzers are 70% efficient, or thereabout. But you said you use 90% of your energy.
Yeah, maybe it's 70. Maybe other electrolyzers are not as much efficient. But you know, you take any percentage. If you have renewable electricity, why would you go and waste that energy for electrolyzing? Just, you know, separating those two elements just to oxidize the hydrogen later on again.
Also, you need, of course, CO2 capture then becomes much more economical because you only have steam and CO2 in the exhaust, yeah?
Yeah.
So I think that you were comparing it to electricity, though. So in the electrical case, you just have CO2, right?
In the electrical case, you even have no water in the steam.
I feel like you're making my case right now for me.
I find electrification very compelling, but it's still a long way to go from my understanding.
Anyway, Bassam, it's good to have an alternative viewpoint.
We'll discuss later.
No, please. You wanted a follow-up?
Well, we did some techno-economics, in fact, and we found that at a price of $2.50 per kilogram of hydrogen, you break even with methane and carbon capture. Now, if we're heading to $1 a kilogram of hydrogen, then potentially sort of you're ahead. Question, of course, this is easy to say. You need storage and you need enough renewable electricity, and it's a whole system. The good thing is you're able to recover 92% of your water to use it back again, so it's not water intensive. And our calculations also show that we could recover 94%, or capture 94% of the CO2. Of course, it's low TRL, but the concept in itself is possible in the future. I'm not saying it's something we could do now, but it's one way by which you could take renewable electricity and turn it directly into a calciner medium that you could then sort of close the loop. And of course, you save CO2 because you're not burning fossil fuels, yeah?
Yeah, what was the, there we go. What was the dollars per ton of CO2 assumption that reached parity with $2.50 per kilogram of hydrogen?
We used $60 a ton, and also looked at the fluctuation in the natural gas price, because it goes up and down all the time.
So you're assuming $2.50 per kilogram of hydrogen.
Of course, the added advantage is that you don't need to store it. It's something that you could produce in situ. It's easier to transfer electrons from where it's being generated renewably to where you want to use it on the plant itself. So the cost and the compression and the transport of the oxygen and the hydrogen is not required, and then you could utilize it. I mean, of course.
So Bassam, I think your point is that under certain assumptions, you think it still has a chance to be feasible, right?
Well, we did the calculations, and I'm happy to share them as well.
So it's actually 5:15, so I think the audience actually has better timekeeping than I do. So thank you very much for your attention today, and thank you again to our panelists.